In the last video, we talked about the general structure of atoms, and we talked about the fact that the nucleus is made up of protons and neutrons, and they're surrounded by a cloud of electrons. Let's look a little bit more deeply at the role of electrons and how they cluster around the nucleus in an atom. So our learning goals are to learn about the structure of the electrons in atoms. As it turns out, those will be very important for us. And the second thing is to learn about the energy shells of the electrons. So when electrons are in atoms, they occupy these clouds around the nucleus. And we're going to call those clouds a region called orbitals. Okay, so we're used to a planet orbiting around the sun or a satellite orbiting around the Earth. Electrons don't orbit around the nucleus in the same way. Instead, they fill space around that nucleus, and because they don't orbit, we call their space, that region, an orbital. So this is what the first couple of orbitals look like for electrons. Okay, the very simplest orbital is the spherical shaped orbital, or the s orbital. Now, you may think that the two pictures on the bottom of this figure don't look very much like a cloud. So if you'd rather look at something that looks more like a cloud, look at the upper one, which is a dot density map of where the electron sits. Now, where the dots are more dense is an indication of where there's a higher probability of finding the electrons. The two pictures at the bottom of this figure are really just meant to give you a sense of what the shape of that cloud is, but not that there is some hard boundary to the cloud. All right, so if we think of the electron as filling a spherical shape in an s orbital, it's most dense at the center, closest to the nucleus, and then it begins to fade out as you move farther from the nucleus. In the other orbital, which is called a p orbital, it looks a little bit like a dumbbell, like sort of weights you might lift at a gym. It has two lobes, and there's a space in the middle where the nucleus is where you won't find the electrons at all. That's a little peculiar. You would think the electrons are attracted to the nucleus, so they'd want to be close to it. It turns out that this is due to the angular momentum properties of the electron. We're not going to really talk about that in this class, but it's important for you to know that the shape of a p orbital looks like this, and it's distinct from the shape of an s orbital. The difference in their shapes is going to make a difference in terms of the kinds of structures they are able to support within molecules. So these electrons don't just pack loosely around the electron. They actually pack around the nucleus in layers. So you can think of it as being like an onion, where you've got some layers of the onion that are closest to the center and other layers that are farther out from that. So the layers that are closest to the nucleus are going to have the strongest attractive forces because they're close to the nucleus. Remember, in Coulomb's law, when you have two charges that are close together, they have a strong force. And in this case, it's going to be a strong attractive force because the nucleus has a positive charge, whereas the electrons have a negative charge. What that means in the case of these electrons is that if you wanted to put energy into the atom and remove an electron, you're working against a very strong force if the electron is down there close to the nucleus. If it's farther away from the nucleus, then you don't have to put in quite as much energy to remove that electron. All right, so this is a way that we can begin to correlate the issues between force and energy. Force is the attraction that the nucleus holds the electron in the atom, and energy is the amount of energy you would have to do to remove that electron against that force. All right, so let's look at an analogy to help see if we can understand that. I want you to think of an atom as being like a hole, and the nucleus represents what's at the bottom of the hole. So now what we're going to do is we're going to fill this hole with electrons, one at a time. And when we put two in, we basically have, if you will, covered up the bottom of the hole. There's no room for more electrons down there. And those two electrons, those two red balls, are closest to the bottom, closest to the nucleus. If we add some more atoms, they'll have to lie on top of those two. All right, and so now the next group of atoms, and it turns out there are 8 of those, they're going to form a layer above the two at the bottom, and they're going to be a little bit farther away from the nucleus. So in other words, it won't take as much energy to remove those electrons from this hole, if you will, or in fact, it won't take as much energy to remove those electrons from the nucleus, from the atom as it is. All right, this continues, and there's a third layer, and you can see that with each successive layer, we have the possibility of adding certainly more electrons, and the energy that it takes to remove those electrons get less and less and less. So as we go higher and higher in the shells, they will have energy to remove them that is less than the one below them. And the ones that are hardest to remove are the ones at the very lowest part of the hole, the first two that we put in. Now we can draw diagrams to help us understand this in terms of atomic structure. A hole isn't exactly like an atom, but these pictures, they're due to Bohr, Niels Bohr, a famous physicist of the early 20th century, and they kind of show how this structure goes about. So the first one has no electrons, so we have no Bohr diagram for that, but the second one with 2 electrons would show a single level, that's a single circle around the nucleus, which has a charge of plus n, and 2 electrons in it. Okay, when we begin to add more electrons in the lower left corner, we now have to add a new circle, a new orbit, if you will, around the nucleus, and that one can hold a total of 8 electrons in it. When we go to the next picture on the lower right, again, we can fit 8 electrons in that level, and it's going to be in another circle further out. So you can see as we're going, we're building electrons that are farther and farther from the nucleus, therefore easier to remove. And the number of electrons that can be accommodated in those outer shells, it's 2 in the first shell, 8 in the second shell, and it turns out to be 8 in the third shell also, though there's a caveat to that, which we'll get into a little bit later. So when we talk about electron shell capacities, each shell represents a different energy level. The capacity of the first level is 2, the capacity of the second level is 8, and the capacity of the third level is 8. It's good to remember this, but we'll find later that this will be indicated by a very simple mnemonic device that all chemists use, namely the periodic table. Subsequent levels have much greater capacities. All right, so this gives you a little bit of a fundamental knowledge of how the electron fills in the atom, and we're going to be dealing with electrons a lot because they're at the center of all bonding between atoms.